All right, so now that at this point, I believe you must have learned and worked with functions long enough, at least at the basic level, that you have worked with functions long enough. So now let me introduce you to one of the major concepts in mathematics. And so we learned that here, we start learning it here, and when you move on to your calculus course later on, you will learn it again, and it will keep happening again in the rest of your mathematical career. So the concept, that big key concept being I'm about to introduce here, is the concept of rates of change. Okay, so we're gonna start out, and this is, since being such a big and key concept right there, allow me to give a fairly large enough amount of details right there. Okay, but I really believe that every detail I'm about to deliver here is worth every single little attention of yours. Okay, so let's dive to it. So now, in my style to approach the concept of rate of change, allow me to stay away from wordy definitions. Okay, so I'm not gonna. You will find a formal worded definition in any textbook. Okay, any standard textbook from a highly credentialed author will count. Okay, so I'm not too worried about a worded the definition of what a rate of change is. Anything that we learn has a definition, but here let's get to the practical side of it, so you will understand what it is. Okay, but through demonstrations and through examples, and through seeing how I'm doing it. Okay, and then you will recognize. All right, so now let me bring up the following demonstration example right here. And it's not a formal example yet, it's just something I bring up as a tool so that we can use and lead it into the concept of what a rate of change is. Okay, so now how about let me introduce this function right here. So we have a function given. All right, at how about f of x equals, so my function here is minus x squared plus 4x, okay, plus 1. All right, it's a function. Now, I don't need anybody to worry about what kind of function this is. I mean, I don't need anyone to worry about that. Whether it's a quadratic function, whether it's a linear function, whether it's a logarithm function, whatever those classes of a function that is, you don't have to worry about that. If you don't know it already, that's good for you. If you don't, it's not something to hold you back from learning this material. Okay, all I need you to see is this is a function. The inputs for this function is the x variable. So anytime we give a value over here, that value is the rule here of this function says we square the inputs and take the negative of the square of the inputs and then add 4 times of the input and plus 1. That's the rule. So I really try to go anywhere we move on with these topics after you have learned about what a function is. I really want to emphasize the fact that any function you're working with is just simply a rule of what to do with the inputs in order to give the outputs. Okay, now another remark I would like to point out is that the concept we are working here particularly focus on those functions where the output is a numerical output. Okay, because I still remember that in earlier video lectures I also brought in the kind of function where it works like a vending machine right there, where the outputs, now in reality out there, some functions give outputs being an object, a product, instead of being a numerical output like what we're working with mostly throughout the math courses. But here, when we're looking at the concept of rate of change, then we're gonna mostly focus on those functions where the output is going to be a numerical value. Okay, and so this is one among those, one function among those that when after you come up with the output, it's a numerical value as well. So you got inputs being a numerical, and you got output coming out also being a numerical. Okay, so now after enough beating around the bush information, so let's get to it. So I'm gonna write from this function. I am going to ask anybody, and for these problems, I'm delivering this lecture in front of the camera, but I highly recommend that you work as independently as possible. So I ask anyone doing this, following with this video lesson, to do the following calculation for me. So how about let's evaluate, just simply an evaluation. And this kind of work should be fluent for anyone learning with me about function up to this point. Okay, so in order to evaluate And I want my students and I want my viewers to evaluate this for me. Okay, and you can take that as an independent trial right there. All right, so now with this function right here, when we're giving the input 1, right, then at least the calculation comes out as the following. So minus 1 all squared plus 4 times 1 plus 1, because that's what the rule says. Okay, and allow me not to get into too far details here. So final calculation of this is going to give me a 4. And this is what I meant earlier by the output here as being numerical outputs. Okay, so we had inputs being 1, and we had outputs being 4. Okay, so that's one problem. Okay, and again, anyone viewing this video lesson should be fluent with how we evaluate an output based on a given input. Okay, and so now let's try again. So I'm going to evaluate. How about I ask viewers, I ask students of mine to do another evaluation problem. So how about I'm going to suggest f of 2. All right, and so with this problem, how about it's as according to the rule, and you can try independently. Minus 2 all squared plus 4 times 2 plus 1. Okay, and so that's the setup for the calculation, and then you can independently get your own answer. The final answer that comes out from here should be, that would make positive 5. Okay, that's the output. And again, this is what I said earlier, that we're working with those functions, and this is one among them. We're working with those functions where the output values are numerical values. Okay, numerical outcomes. Here it has it's a quantity. It represents a numerical quantity. Okay, and so now, and so now what we're looking into after all of this work right here. So we came to the following summary. F of 1 equals 4, and f of 2 equals 5. Okay, and how about one more? F of 0. Okay, so quick little scratch work. F of 0 equals, the way how we're doing it, 0 squared minus 0 squared plus 4 times 0 plus 1. And the answer is easy enough, 1 as the numerical outcome right here, the final numerical answer. So the output for this is 1. Okay, and so now when it gets to this, allow me to explain as graphically as possible. So that was just the pure computational side of that. Okay, let me now bring that on a graph right here. And at this point, anyone is well aware that any function has a graph. So this function here has a graph. You can use your favorite graphing device right here to quickly pop out with the graph of this particular function. We're not particularly studying about the graph of this function, but we just assume that, hey, after we know that this function has a graph, let's look at these values on the graph. Okay, so now the graph of this function is the following. All right, so this is the graph of our function minus x squared plus 4x plus 1, the graph for f of x right here. So we had, let's look at the following point right here. See, this was that point 0, 1, where the input is 0 and the output is 1. Now we've spent some time looking at we've had lessons before this where I explained, hopefully thoroughly enough or in details enough, that the idea of looking at a graph is that the vertical values, the vertical heights represent the output values of a function. Okay, the vertical height represents the output value of a function, and then the horizontal coordinates, the horizontal value on the graph, represents the input. So it's just an international thing, an international agreement, okay, an international rule that we put input values of a function on a horizontal scale, and the output values we put it on the vertical scale, and that's how you saw that consequently on the graph. That's why now when input equals 0, when input x equals 0, we have an output being 1, which is right here. And so we had another one. Okay, so we came to input being 1 earlier. Okay, we came to input 1, and that's what the label here is telling us right there. So when the input x equals 1, then we had that output 4 just consistent with the value we calculated on the table earlier. I mean on this on the board space earlier. All right, and so now just like that, when x equals 2 and the output for the input being 2, we came out with output being 5, and that's how we consequently had a point on the graph. And this is where we had that value. Okay, so now that point here just popped to a different place right there. It just got changed to a different place. And I just start saying that word, it got changed to a different place. And we will dive in further to that. Okay, so 2, 5, input 2, output is 5. And that's how we're reading this graph right here. Okay. My point now of this illustration problem is not to make anyone repeat the work, to substitute in a value and coming out with an output. That's we've done with that at the end of the earlier lessons, okay, long ago. Okay, that's so the aim of this demonstration problem is not to make anyone repeat your work in calculating. That's why I was I was much faster than how it was when I was teaching about evaluating function. The main aim of this, now you're seeing that one function, but just now look at the inputs itself. You see, when I started out, this is my start, okay, and everything has a certain order. I mean, anything we're doing in life has an order. What comes first, what comes next, okay? So just in that order, see, I started out with this value, and then what? And then I changed to a different value. I start out with a value, and I change to a different value. Okay, and I change to another value. So there it's. I'm starting to make you realize. I'm starting to make any viewers to realize that there's always changes. We have a lot of times we have to change our input values. Okay, and that's the whole big point of having a function. Once we have our function defined, we want to see how our function changes from an input to a different input. Okay, to another input. We want to change from an input to a different input, and along the way, so at this point now, as we change the inputs to different values right there, the outputs will also change accordingly. Okay, so I repeat, the whole point of having a function is that we want to investigate, we want to study, and this is what you will study. This kind of problem will keep coming back with you no matter how high and how far you would advance in your mathematical career right there. Once you have a function given, starting out with a given input value, we're going to start studying the change as we change to different inputs. So starting out with 1, I started out with 1 and I changed to x equals 2, and then I changed back down to x equals 0 right there. Okay, so these changes, along with these changes, because we independently change the input value, and then along the way the output value changes depending on how we change these inputs right there. Okay, and so now, so I start bringing in to make people realize that there's changes happening all over. Okay, so now back on the graph again. You see, when we change from x equals 0, I mean, this is our starting point right there. First we were here. First I was here. I brought up that problem when this is f of this height right here is f of 1. Okay, but specifically the input is 1, and so that's 1, 4 right there. Input 1, output 4, and then in the very following problem, I change to x equals 2. See, f of 2, and we had output 5. So from here to here, see right in front of your eyes right there, when you're seeing this graph and looking at closely at that point right there, and you notice a change. That point jumped from x equals 1. Okay, from x equals 1, and then that point jumped, made a change to x equals 2. So the point itself made some change. So the change now happens there. If we are now looking a little more closely, the change and it was also reflected through this work that we're organizing here. There was not only one change. There was the change in the inputs. Okay, I changed from x equals 1 to x equals 2. There was a change in the inputs. And along the way, there was also another change that just happened naturally, consequently, along the way. There's a change in the outputs right there. Okay, so on my graph demonstration again, you see from x equals 1, the point is here. And now if we change to a different input, x equals 2, the point is here. So just simply noticing a jump in the point from here to here. There are actually two kinds of changes. Okay, two kinds of changes. There's a change in the x values, the input values, and there's a change in the output values. Okay, there's a change in the input values and there's a change in the output values. There are always two changes anytime that we switch from an input to an output. You see, for us here, it's very natural that we just look at that we immediately sense the change in the inputs, because we change it ourselves. We change from x equals 1 to x equals 2. We make those changes ourselves. But then as we make those changes, the function will also change its values. The vertical values will also change. And that's another one that I want to make my students to realize, the people who view this lesson here to realize that. So as we independently change the inputs from one input to another input, okay, there's the change in the outputs along the way. All right, and so now I want to emphasize another important understanding. So yes, we're looking at changes, but let's put things in a certain order, okay? So now for the change in the inputs, x right here, and let's stick with for simplicity, let's stay with the tradition where we use x as the input, and in this function, x is the input. So the change in x, okay? Now for changing x, let's organize the change from smaller to larger, okay, from smaller to larger. So the change in x here, I'm seeing that I can think from x equals 1 to x equals 2. So my point is, anytime we're looking at the change, we want to see the change as having a start at a lower value and then ending the change at a higher value of the input. Now right now I'm talking about the change in x. Okay, so the change in x, we always want to set ourselves in that convention that the starts of the change, we begin at a lower value and then we ending at a higher value. And that's how we see a change. Okay, because yes, admittedly, according to the order of the work here, I started out with a 1, I switched to a 2, and then I switched back to a 0. So it's a little bit out of order, but that's just for students, for viewers to understand there are changes. But now to systemize, to make a systematic understanding, then we always gonna put the change in x in a certain order from smaller to larger. Okay, start at a smaller value and then ending at a higher value, at a larger value. Okay, or it's in increasing order. Okay, and so now. So you can also look at the change that you can start your change in x. You can start at x equals 0, and then you end that change at x equals 2. Okay, that's another change right there. Okay, and then you can change from x equals 0 to x equals 1. Okay, so like I said, when we're actually making a systematic organization of these changes right here, then we have to, now in math, we have to put all these changes to reflect the fact that the change starts at a lower value and ending with a higher value. Lower value and ending the change at a higher value. Lower value and ending at higher value like that. So any of these is now a legal way of looking at a change in the x value in the inputs. Okay, and so now, so that's the change in x. And so now, I'm going to need to quickly put this away. And let's now just look at the one particular change in x. Okay? So for the change in x that let's specifically look at start at x equals 1 to x equals 2, for example. Okay, so for that change in x, now, as I mentioned earlier, along with this change, we realized there was a change in the output vertical value. So in this case, we also noticed there was a change in the y value, the outputs, the vertical value right there, the output values. And so now you see when x when x equals 1, then the y value there was f of 1. And that's why I still have this value right here. And then this is start, and then it changed to y equals f of 2. Okay, so it's a convention. Again, I have to emphasize, for the change in the input values, we always want to set the change in the order from small to large. Okay, start to end from small to large. But for changing y, we can let go. We can let go of that requirements. We don't need to put the change in y in the order from small to large like that, for a good reason. Because the change in y depends on the change in x. So for x, we always want to put the change in the order, right? Start to end from small to larger. But then for the change in y, we want to leave that just how it is. When x is small, sometimes y is small, but when x is large, sometimes y is even smaller. So we want to see all kinds of different ways of changing like that. Okay, and so now put a note in here for me. Okay, so changing x, we're going to go increasing order. Okay, or we want to go another way of saying left to the right. Okay, that's a different way of saying that, but that's just the way we put as a convention, as a requirement for changing x. But changing y, we can let go of that. Okay, no need for order. Okay, and that's what I meant, because we don't need to specifically put the change in small to large or whatsoever. Okay, and so now, so that's here. I'm just pointing out that there was a change. There was a change in y. There was a change in x. Okay, I was just pointing out. But now we can calculate those changes. That's the next step. So now we realize already that there's a change. There's a change in the x inputs. There's a change in the y inputs accordingly. Okay, so now we're gonna step in and calculate. So now in this specific change right here, I want to change in x change from x equals 1 to x equals 2. How much change? How much change? So now in that way, how much change is easily, and so now again change. In x, now I'm actually calculating it. So it's not like I'm labeling it anymore. It's not like I'm just making realization about it. Now once we have already realized, we're going to start calculating it, changing x, changing the inputs. So to calculate a change, you don't have to wait until pre-calculus to understand, but it's just simply the difference in the value between 2 and 1 right there. Okay, and so in that way, we're going to go with 2, which is the final x value, minus 1. So now we formally take that difference to calculate how much change between x equals 1, from x equals 1 to x equals 2. Okay, and so now a couple terminologies here that comes out. So change in x itself is already a terminology. But now I put that in the red box. So this 2 right here is called the final x, okay, or the final inputs. Okay, and then this 1 right here is called initial. Okay, the initial x value, or just in the initial inputs. Okay, because we change from x equals 1 to x equals 2. And the work to find out, the work to calculate how much change has gone by is the 2 minus 1. Final x minus initial x. Final x minus initial x. And that's a set rule for that. That's to calculate the change in x. Okay, and so now, when it comes to changing y, when it comes to change in y. Okay, when it comes to change in y, we can also calculate that. So earlier on the other board, I was just pointing out, I was only pointing out to make people, to make students of mine realize that there was a change anytime that we have two different values. But now to actually calculate that, right? Change in y can be calculated as. So now things need to be done a little more cautiously now. That you see, the final y value is the whatever output that came out from the final x. Okay, so in that way, final y value here for this particular problem, it was 5. This is the final y. Okay, I'm going to subtract the initial y. So we started to already realize that there's a rule. It's always the final minus the final value minus the initial value. So here we're looking for the change in y. So it's the final y value minus the initial y value being 4 over here. Okay. So as far as the interpretation, okay, then all this here really was f of 2 minus f of 1 here. See, the final y value, or what it was, 5, but really it's the function value at the initial, at the final x, minus the function value at the initial input right there. All right, so now this is how I'm seeing it. Okay, this is final y value or output minus the initial y value. Okay, or this is also referred as final output. Yeah. All right. So now there's a change in y and there's a change in x. Okay, two separate changes, and we have just now calculated it here. So the change in x in this case, is 1. So this 1 here is not the same as that 1. This is just the initial input, but this is how much change from this initial input to that final input. The change in y here comes out also equal 1. Okay, but that's reflecting that the function value at x equals 1, initially the function output value is 4, and it changed to 5, so the total change was a 1. Okay, it changed in value by 1. Okay, so now let's have a look at that on the graph before I get too far. Okay, so on the graph here, you see, when the function input is 1, we have that, and let me put that vertical dotted line here to make it clear that, you see, this is where function input is 1. Okay, and now I change to x equals 2. So the point jumped to a different point right here, but at least what we see right in the graph right here is the input is changed to x equals 2. So now from x equals 1 to x equals 2, okay, x equals 1 to x equals 2, the total change is this difference right here, which is this grid right here being 1 in length. So this space, this amount of width between x equals 1 and x equals 2, this amount of width right here is that change in x right here, is that change in x that I calculated to be this quantity right here. So this is how much change that was gone by. Okay, after we calculated final input minus initial input. Okay, and so now that's how much change in the x value as a quantity. So just that same way we also calculated the change in y, okay, by doing final y value minus initial y value, and correspondingly it means f of 2, f at the final input x minus f at the initial input x right here. Okay, and we came out to a change being 1 as well. All right, so let's look at that on the graph to understand. So with that change, so now observe my point carefully right here, and I'm hiding away the vertical line, but now I'm showing a horizontal line. So right now at the initial input x equals 1, we're at the height being 4 for the outputs. So the outputs being 4 initially. And then when x is changed to x equals 2, okay, that's where the point here is. The height is no longer 4, the height is now changed to, y equals 5 right here, y equals 5. Okay, so now with this, that's why the change in the output value has been exactly 1 vertical unit right here, 1 vertical unit that's being reflected and seen in the grid right here. All right, and that's the whole idea about the changing y and changing x, and that's the meaning of this value 1 right here. Okay, so this is 1 square over. Now I'm starting to use that term over simply because when we're looking at the change, in x right here, we always set ourselves in that convention, in that requirement that we're putting x values in increasing order from the left to the right. Okay, we're always looking at the graph from the left to the right. Now, always is maybe not that precise way of saying it, but a big percent of times we're looking at the graph from the left to the right. And so specifically when we're calculating changes, then it's a good requirement. It's a requirement that we're looking at x value, input values changes from the left to the right, okay? Smaller value to the larger value, increasing order from the left to the right. Okay, and so now in that way, now I have to erase this space right here. So I just now pointed out that there are changes in the x values and changes in the y value. And then along the way, we were able to calculate those changes as 2 separate quantities, okay? 2 separate quantities. So what does that mean by a rate of change? Okay, the rate of change. So here, that change in x, okay, that we calculated being 1, that change in y that we calculated also being 1. Okay, we're gonna purposely set up a ratio. It's a ratio, so that change in y we calculated being 1, that change in x we calculated being 1. Okay, and so that consequently gave us a ratio 1 over 1. So this was the change in y over the change in x. Okay, and so this ratio overall, well, as a final numerical outcome, as a final numerical value, it's a 1. But so now, ladies and gentlemen, this is called the rate, because it's a ratio, it's a fraction, okay, a rate of change. Okay, all right, and to be precise, it should be the rate of changes right here, because there are always 2 changes, the rate of 2 change. Okay, so the change in the outputs over the change in the inputs. And now let's not rushly take that and then erase and then move on to the next thing. I want you to carefully look at this. When it comes to rate of change, we always want this ratio to have rate of change in the outputs being in the numerator. Okay, so we're talking about changing y per change in x right there, change in the outputs per units of change in the inputs. So it's always changing y over changing x. Okay, so ladies and gentlemen, this ratio right here, see, that's why we call it, it's a rate. Changing the y value over the changing x value. Yes, now we call that, that's what it is. It's the rate of change right here. Okay, all right, so now to be a little more specific, this rate of changes, okay, or this, for short, this rate of change right here, this rate of change happened in the interval from x equals 1 to x equals 2. Okay, that's another specific information, because we had this rate simply because we look at our initial x value from 1 and then our final x value at 2 right there. And so we had this. But then for a different 2 values of input and output, I mean 2 values of initial inputs and final inputs, we can have a different rate of change. Okay, And so now, how about, let me quickly erase this away. All right, so the same function right here. Now I can look at another one. Let's now look at the rate of change. Okay, from, how about x equals 0 to x equals 2, for example. Okay, so the wording is making it clear. So x is changing from x equals 0 to x equals 2 right here. Okay, so now, so quickly we can calculate my change in x. So of course now we realize already that there's a change in x input. So let's not beat around the bush anymore. Get straight into the idea. Now we're calculating how much change in x value. Final minus initial. Final input minus initial. All right, so that quantity, that amount of change is 2. Okay, but that's only one change. That's just the change in x. And now let's look at, and then on the other hand, we have to do, admittedly, it is a little bit counterintuitive in the sense that we always start out with calculating the change in the x first, and then we calculate the change in the y, and then at the end when we're setting up as a ratio, we put the change in y on top. So that's the part that where it is a little bit counterintuitive. Okay. So now the change in y is going to be, you see, the y value at 2 at the final inputs, the y value at the final input minus the y value at the initial input. Okay, so see, this is initial input, okay, and this is final input. All right, so we always go with final minus initial. So final inputs minus initial inputs. Final outputs, meaning the function value at final inputs, minus initial outputs, meaning the function value at initial inputs, like that. And so that was in my, if I remember correctly, f at 2 was a 5, f at 0 is a 1. Okay, and so now in that way, we're looking at this is the total change in y right here, 4. Okay. I didn't get to the final answer yet, but let's quickly swing over to the graph and have a look. All right, so when x equals 0, and now let me put both lines right here. When x equals 0, y equals 1. Okay, just like how it was stated here. When x equals 0, y equals 1. And we made that list earlier, and I had to erase it to make space here. X equals 0, and consequently y equals 1. When x equals 2, when x equals 2, okay, when x equals 2, y equals 5, the output is 5. So this is final input, final output right here. Okay, and so the change now for x, the change, look at my vertical line. First vertical line is at x equals 0, but then at the end it's x equals 2. So the change here is 2. Okay, this change here is 2, and that's what it is for this change amount right here. This is how much change in the x value. Okay, and then what's that for? How do I see that for on the graph? Okay, so on the graph, y equals 1 is here. Okay, or this is f at 0. This is f at 2, f at 2, f at 1. So my point rise from y equals 0 to y equals 5 right here. I meant to say my point rise from y equals 1. Okay, y equals 1 to y equals 5. So the total rise was about 4 right here. Okay, and so that's what it is. And for now, it's just something that comes natural. So to allow me to Just for now, I just want anyone to take note of this. For the y value, it's a positive change there. Okay. Now, in the way how we calculating the change in x, it will always be positive because we always go with final value being larger than the initial value. As I said earlier, we always going to put the change on the x, on the inputs, increasingly from small to large, okay, increasing from the left to the right. So that means the final input is always larger than the initial inputs. So changing x is always positive. But changing y, since we didn't have to stay in that requirements about small on the left and large on the right, or increasing order, we didn't have to do that, and so it could be positive for the change. In some other case, it could be a negative change. Yeah. Okay. So later, and we will get more to that. Just for now, right now, since we're quite beginning over here, then all I see is as an observation. The change in the y value in this change from 0, x equals 0 to x equals 2 right here, that we had a change on y value being positive 4. Okay, so I show the two separate changes, and now the real rate of change I'm looking at now. All right, so now allow me to write it down. Let's use this space right here. All right, so the rate of change. Okay, really equals. But now, once we're putting it in a rate, then we have to always put the change in y over change in x. Okay, change in y over change in x. Okay, so in that way, consequently, for this particular problem, the change in y was 4 squares, and it was a positive change, and we divided that by 2, which was the change in the x value, 2 squares over, okay, and then we had, in this case, it was a positive change, so it was a rise. Okay, so eventually I will make all of those connections that you have seen before. Okay, so now 4 over 2 is in the end reduced down to a 2 right there. Okay, so ladies and gentlemen, as x changes, as x value changes from x equals 2 to from x equals 0 to x equals 2, our y value changes from 1 to 5 right there, and it made a total change of 4. And so we had a rate of change. We had a ratio of change saying that the y value changes. Okay, the y value changes 4 per 2 changes in the x value. So in the end, we came to a ratio 2 over 1 like that, and that's what it is. And it's called, so it's a rate of change. Okay, so now before I move on to formal examples and all that, so let's make some connection. Believe me, before you view this lesson, you must have seen this somewhere here and there, and maybe that you have seen it in a brief introduction. That's understandable, because when you're at a math course before pre-calculus, then you only need to be briefly introduced to the idea. Okay, and here it's my job to make it all formal, and then you're going to carry this into a formal calculus course later, or even higher in your mathematical career. Okay, so here I'm going to put in a lot of details, but now you're going to start clicking with how it's connected with those information you have learned in your previous course right here. You might have heard a lot about rise over run. Rise over run. This is what it is. You see, this change in x, it's always running from the left to the right, because didn't I say earlier that we're always going to put our change in the x increasingly from the left to the right? So final x is always larger than initial x. Let me demonstrate that again through the graph. See, we always going to put, and the way it is graphically, x values happens increasingly from the left to the right. So in initial change, we always going to go for the change. The initial value is always placed on the left hand side, and the final value is placed to the right hand side. So on the x-axis, for the inputs, we set ourselves in that requirements that lower values on the left and higher value on the right. So we start at a lower and we're ending with a higher. We don't want to go backward, okay? We don't want to go from large to small. We always want to go from small to large, from the left to the right, okay? And so in that way, change in x will always be positive, okay? But now change in y. In this problem, in this particular problem, the way how our function is, we see that the function is rising. How do I know it's rising? Because the change in y value is a positive. That's why in this case right here, it's a rise right here. That's why in this problem, it's a, now I'm noting this. This is a rise over run. It's a rise over run. You must have seen that. Okay, rise over run. So it will always be a run. But then in this problem, it's a rise. So you notice already, initially it was at a lower value or at some y value. Okay, and then at the final x, when it changed to x equals 2, the y value changed higher compared to where it was vertically originally. And that's why it was a rise. Okay, all right. But then in other problems, so let's find out. So now we've had one problem done. It's not even a formal example yet, okay? But I'm slowly getting all that and putting all the pieces together, and then at the end we are going to put in a total formulation of how we get these done. But at least up to this point, you already realize clearly what a rate of change is, okay? So now how about same function here, okay? Let's calculate, let's look for rate of change, or sometimes I see that as rate of changes, because for me personally, I always see two changes, okay? So quite a few textbooks just indicate rate of change, but I want to see it as rate of changes, okay? And so now I want to see, let's calculate the rate of changes from x equals 2 to x equals 4. X equals 2 to x equals 4. Okay, x equals 2 to x equals 4. So we don't need to rush into a formula or anything like that. And I believe you might have also seen a formula. It seems like I'm moving slower than what you have already seen. But the point is, this class right here you're taking is the whole class where we put all of those little bit details that you have seen earlier into a formal lesson, where I have to explain all of those detailed explanations. And then we're going to, again, put that into a formal formula for you to calculate the rate of changes. Okay, so here allow me to still, explaining all the concepts and the fundamental understandings of that. Okay, so now here I see there's a change from x equals 2 to x equals 4. So yes, we take very natural, we're going to calculate the change in x first, because it's given right here in the problem. Okay, it's given right there. So changing x. Now, how do we calculate that? Okay. Final x is 4 minus initial x is 2. Final input minus initial input. Okay. And now since I'm seeing changing x here, not only a title, but as an actual quantity now. Okay, as an actual quantity. And so I can see that changing x as a lengthy quantity equal 4 minus 2. Final inputs minus initial inputs. Okay, and so now that gives me a total change being 2. See, changing x will always be positive. That's why it's a run. Yes, you are now welcome to see this as a run, because it's always a positive change. We change from a lower value to a higher value. Okay, but now let's proceed. Let's advance to calculating the change in the y value. And see, there are always two changes. Okay, there's always a pair of changes. Okay, so changing y, you see, final y value, final output is determined by the function at 4. So f of 4 minus the initial function. See, it's always final minus initial. So I keep putting those details into your mind up to this point. And then initial function value right here is f at 2. Final output is the whole f of 4 minus final minus initial output f of 2. Okay, and so now calculating it, f of 4. Now anyone viewing this video can go ahead and help me calculating this. Okay, and so that is going to give me a positive 1, and you can always double check with me. This is final output. Initial output here, f of 2, we had that being 5. Okay, and then we subtract. See, so this is making it consistent with what I said earlier. We don't have to put final and initial. On the outputs, we don't have to put final and initial in the rule that the final have to always be bigger than the initial. Okay, we don't have that. We don't have to worry about that requirement. So here, obviously, final value is smaller than the initial output value right here, because on the y value for the outputs, we can let go of that requirements. Okay, because that's the point we want to see if the function is rising up or falling down right there, and I will get even further on to that. Okay, so now at least, but back to just the calculation, the final outputs minus the initial output right here, that gives me a negative 4. Let me make this negative sign really attention catching right here. Negative 4. All right, so as far as just calculating the changes, we have calculated both of them. Changing x, changing y. I'm now going to switch over to the other board and get the rates, because this is not the rate yet. This is just the 2 parts right here. All right, so now for x changes from 2 to 4, then our rate of change is done as following. This is now actually the formula to highlight already, the rule to highlight anytime you would like to calculate the rate of change. Okay, and so now changing y, it was a negative 4. Changing x was 2. Okay, and so ladies and gentlemen, unlike the earlier case that I have done, this time now the change in y was not a rise, it fell. Okay, so here I call it a fall. Okay, for students who got out of a course prior to pre-calculus course, they tend to say it through the mouth as a habit, rise over run, rise over run. But the real truth behind is that there could be rise over run, or that could also be a fall over run like that. Okay, things don't always go as a rise over run. Okay, because the idea is for the change in x, we will always have a positive change, and you already seen all that reason. But now because of that, okay, the y can change accordingly. So sometimes it's a rising in a y value, sometimes it's a falling in a y value. Obviously, in this case, it's a fall. Okay, overrun. So now our final ratio, it's a minus 4 over 2, which is numerically negative 2. Okay. Let's see that demonstration in the graph, through the graph right here, to get yourself really convinced about what I meant by it's a fall instead of a rise like that. Okay, so now on the graph here, this is the graph for the function. All right, so initially we're at x equals 2. That's why I have the vertical line here right at x equals 2 and the horizontal line to indicate y equals 5, the output right there. And now I'm going to change from x equals 2 to x equals 4. You see how the motion, the change of my point right there? Okay, so my point now is changed to x equals 4. And now the y value came out to be 1 according to the calculation. And now the graph is representing it. Okay, but now if we're looking at this picture here, graphically speaking, then you see the change will always be from the left to the right, or again, the positive change in the x value. That's why it's a run. We run from the left to the right. Okay, but now as far as the y value vertically, our point dropped. Okay, our point vertically dropped from high, from being 5 up high, and it dropped down, okay, to 1 right there. So it made a change, but now it's a negative change. And let me put it back in closed zoom again. And let me put it back in close full view zoom right here. Okay, and so the change here, the change was 4 squares vertically, but it's a drop, it's a fall right here because it starts high and it's ending with low right here. All right, and that's the reason why in this case I demonstrated that the final rate right here, this final rate is a fall over run. Okay. All right, so now it's time to formalize all that idea right here. I'm still not going to give a worded the definition. You already know what a rate of changes is. Okay, you already know what a rate of changes is. But let's just make things a little more systematic. Right? That's all. To get any one of my students or viewers who want to do rate of change to start setting yourself into a common routine of how you can calculate rate of change. Okay. And so just right here in the problem, you see, anytime calculating rate of change, you have to be given, or sometimes it could be your own problem that you are looking into it. You're looking into calculating rate of changes on your own. Then you have to know you see from initial to final right here, what you have here is an interval of change, an interval of change in the x values in the inputs. Okay, so from some value initially to an ending inputs finally. Okay, this is an interval. All that here, okay, it's an interval. We always have an interval of x value. Okay, an interval of x values, and then the actual work to calculate is here. We calculate the change in x, and then we calculate the change in y. Two separate works. And then in the end, we put that in that ratio you have seen over there on the other board. The change in y over the change in x. Okay? But then admittedly, the method I've been explaining, it doesn't work for anyone because it's too long. It takes too much thinking process. Okay? It takes just too much thinking process. I mean, technically that's what it is. That's the foundation. But now to keep things in a very organized and systematic method, to set anyone into a systematic method right there. Let's see the following. So now just the same problem. I'm calculating. Now formally the problem would be worded as following. Calculate, right, rate of changes. Rate of changes over the interval from 2 to 4. You see, in a shortened form right here, this is how that problem calculates the rate of changes over that interval from 2 to 4. That's just simply a different way of saying, see, it's a rate of changes from x equals 2 to x equals 4. See, the long form of saying that, now we have a more symbolic form, a better symbolic form of saying it's the rate of changes over that interval, 2, 4. Okay, or sometimes you can say on that interval. Okay, these two words can be used interchangeably. Okay, but now to really formulate into a solid method right here, that rate of change we calculating there, see, this is the fundamental. But we don't want to stick with the fundamentals all the time because it's too lengthy. Okay, so now right from that fundamental, you can see that we need to calculate the change in the x, right? So one way of saying this, x2 for the final divided minus x1 for the initial. So x2 is the final, x1 is the initial. I did this work here when I had to teach the fundamentals earlier. I calculated the two values, the change in x and the change in y separately. So 4 here, if 4 here is the final x, this is now x2. Okay? And then if this 2 right here is the initial inputs, the initial x, that was x1. That's the whole idea behind the scenes right there. Okay? And then so in that way, changing y, okay, you can call this f of x2 minus f of x1. Okay? And even shorter, you can call this y2 minus y1. Okay? final, changing y, final y value minus initial y value, or the final function output minus the initial function's output like that. Okay, so now back into that formula that I'm about to derive right here. So rate of change, right? Rate of change is one way you can say f of x2 minus f of x1. That's one way of doing that. Okay. That's one way of setting up. So this is a one widely used formula. Rate of change is equals f of x2 minus f of x1 over x2 minus x1. And so in this particular problem, our x2 is 4, our x1 is 2. So in that case, bringing in this actual interval, we're looking at f of 4 minus f of 2 divided by 4 minus 2. That's how we, so now I'm getting through with that solid method right here, how to calculate rate of change for any function on any given interval. Okay, and then that's how I ended up with, earlier, you see in the denominator, this is the change in x. So that's how I ended up with 2, and f of 4 here was a 1 minus f of 2 here is a 5, and that's how we ended up with negative 4 over 2, and consequently a negative 2. Okay, but this is how we're getting things done formally, okay, and structurally. Okay, you don't need, I mean, as a formal written work, if any instructor is collecting written work from the students, including me as an instructor, all I'm expecting is the setup right here. You don't have to tear things down as calculating changing x separately like this, even though you're welcome to, but formally speaking, writing things in the other way looks a lot more neat, okay? You don't have to do two separate, changing x and changing y. That's just for instructional purpose only. Okay, that's for instructors to give a clear and solid understanding. All right, and now that same formula that now I just used right here, alternatively, see, alternatively. So this is the solid one, f of x2 minus f of x1 over x2 minus x1. But then alternatively, people can come up with a few, I mean, some other the variations of that formula. It's just a variation. Okay, so another alternative form. Another alternative form of that, just rate of change. All right, so rate of change is simply, you see, y2 minus y1. Okay, over x2 minus x1. That's another way of seeing it. All right. Some textbook authors write their formula as following. Rate of changes equals y final. So the subscript f here stands for final, minus y initial. So the subscript y right here indicating the initial is short for initial, divided by x final minus x initial. You see this rate of change kind of formula a lot in, if any of you are taking a physics course concurrently, okay? But in math courses, you see this formula a lot more often. Okay, and then the same rate of change, see, rate of change, it's a change, it's a difference, minus right here, it's a difference. It's a difference, again, difference in x, I mean difference in y over difference in x, difference in y over difference in x, difference in outputs over difference in inputs, because changes is calculated formally as a difference, okay? And so now, even furthermore, this is just for you to be aware about different ways how you have different textbooks, presenting your understanding. Okay, I hope I can make that comprehensive enough, but the point of this lecture here is that you can find this corresponding lecture here in any textbook that you're using, any standard textbook that you're using. You don't have to tie yourself down to any particular textbook. This lecture can be used for, in addition to any textbook, corresponding to any textbook. And so even some textbooks, for some textbooks, the author, they use, so now just like how I was saying it earlier, a difference, okay? The changes, any change is calculated as a difference. So here I see a difference. And so difference is notated by a delta symbol right here. Delta is a famous Greek symbol. It's a capital letter D, by the way. Okay, it's a capital letter D. Okay, in Greek. Okay, but that's a famously or traditionally capital letter D in Greek. This delta right here is used to represent a difference, a change, a difference. That's why the difference in y2 and minus y1, the difference y2 minus y1, for short, for convenience purpose, a lot of times many textbooks, authors write this difference here as a delta y right here, difference in y, okay, over delta x. So this is another form of a rate of changes right there. Okay, and the same here. See, it's the exact delta y over delta x. Okay, I'm just trying to show as many notations and symbols as possible. Okay, and as an interpretation, see, sometimes it's a rise over run. Delta x is always a run. Sometimes it's a rise over run, or sometimes it's a fall over run. Fall or rise, it's just the delta y right here. It's deciding fall or rise. If it's a positive, like you have seen in the demonstration earlier, if it was a positive delta y, okay, then it's a rise over run. If it was a negative, like the one that we're still having on the board, on the other board here, it's a negative delta y right here. See, 1 minus 5 is a delta y. 4 minus 2 here is a delta x. So delta x is always positive, but in case delta y is negative, like this case, it's a fall over run. Okay. All right. So now that's the fundamental of all of those what it means by being a rate of change and how we're doing it. So after this, we're going to start getting into some formal examples where you start getting comfortable to using this solid methods to calculate a rate of change at any point in your mathematical work. Okay? All right, so we are now ready for our first formal example. Okay, so here we are at example 1 right here. All right, so let me now write down the wording instruction of the example. So here we are given a function. So let f of x be defined as about x squared minus 1 over x. Okay, so here's our function. F of x equals x squared minus 1 over x. The x here is the input, right? And the once we have an input given in, this rule determines how we calculate the output. Okay, and so now once we have that function given, we want to compute. Okay. And here I'm using that term compute, but in some other textbook, in some other case, we might use the term evaluate. Okay, evaluate. So compute or evaluate, different words here being used scatteredly throughout the different textbooks out there. Okay, so compute or evaluate the rate of change. Okay, the rate of change. Okay. And so now, right after that, I'm going to break it down into part A right here. So we want to calculate the rate of change on the interval. Okay, on the interval from 2 to 4. All right, so now once we have this problem given, then all that information we've learned prior to this point now is going to apply. Okay, so from what we've learned just now, right before we got into the example, then rate of change, we are going to have two changes. There's a change in the x values changes. The x value changes from 2 to 4. And then according to that, accordingly, the y value changes. And so in the end, the rate of change. And notice how I call that rate of changes, scatteredly here and there prior to this example. But for now, allow me to use the proper term where most textbooks are using. Okay? Rate of change. And I will explain that the reason why I went with plural sometimes, and then now formally speaking throughout all examples and problems out there, textbooks are using the term rate of change in singular formula here, and I will get to all that. Okay, but so rate of change, the way we find that, again, so in this interval, in how I explained earlier, along with what I have explained earlier, 4 is the final x value, the final input, whereas 2 here is the initial input. And so the fundamental formula that we use here is rate of change equal the function value at the final input, or in other words, the final function's output subtract the initial function's output, f at 2, or f of 2. And then we're dividing that by 4 minus 2. On top here, what we have here is the change in the y value, or delta y, or y2 minus y1, or yf minus yi. Okay? In the denominator here, we're looking at final x minus initial x, or x2 minus x1, or delta x. Okay? So many ways of seeing those. Okay, so that's the starting setup for calculating the rate of change. Okay, and so now the next step is just simply to proceed into the actual calculation. So on this space of my board right here, let's look at, so we can, anyone doing this kind of work is welcome to tear the problem down to each individual part, just like how I've done that in the earlier part. So, but now this part here belongs to scratch work. F of 4, okay, is simply going to be a 4 square minus 1/4. Okay, that's how, that's the computation that lands into the output of f of 4. So that gives us, so is this a 16 minus 1/4? Okay, I'll leave it there for now. And then f of 2 equals 2 square minus 1/2. Okay, and so 2 square minus 1/2, that gives me a 4 minus 1/2. And so now really for the rate of change I was talking about, so this rate of change must be equal to, so the 16 minus 1/4, this is f at 4, f of 4, and then I'm going to subtract 4 minus 1/2. Okay, and that is f of 2. Okay, and so now after that, and well, in the denominator here, we're looking at 4 minus 2, and that's simple enough, so I didn't need to tear it down separately. Okay, so this work here is highly recommended to be on scratch work like that, whereas you can directly substitute values in and do a direct calculation on here. Okay, anyone is welcome to do this, but keep that in scratch work. So now, as we proceed further into the calculation, so now in the numerator there, we're looking at 16 minus 1/4 minus 4 and plus 1/2. And I don't even need to really spend time doing all of these things step by step, because anyone following along with this video should be mature enough in order to see this. Okay, so our final answer comes out, well, our reduced answer right now comes out being, so that's an over 2, and 12 plus a 1/4. And now making denominator and all that, it gives me a 49 over 8. Okay, so this is our rate of change over the interval from 2 to 4. Okay. All right, so that rate of change here is 49 over 8. Then we have found our answer. So let's now look into part B right here. So again, I am just simply giving a different interval. And by the way, in the earlier example, the rate of change here was a positive rate of change, so you can think of that as a rise over run. Okay, because the change in the y value was a positive change. Okay, so now in part B right here, let's compute or evaluate the rate of change on the interval about 1 to 3. Okay, on interval from 1 to 3. Okay, so once again, you can see that the structure, the wording of this problem is exactly the same like how we were doing that back in part A right there. So I can start picking up pace right here. It's just the only difference here is that I switched to a different interval. Okay, and so the rate of change as a starting out point right here, the rate of change, and allowed me to again use a proper term that's being used throughout all textbooks, all standard textbooks out there. It's the rate of change in plural, in singular. Okay, and I will explain the reason why I was using plural in a few times the scatter around my earlier part of the lecture, and now I'm gonna come back. I just now come back and use the exact same term as how many textbooks are using. Okay, so now rate of change, but it's just that exact same fundamental we've been doing. Okay, and I will give that explanation later of why there was a little bit difference between what I'm teaching, and in the end it's all meeting together. So rate of change here, we're calculating, I need f of 3. The final function's output minus the initial function's output. That means f of 3 is the final function's output minus f of 1. And then final x value, final inputs minus initial inputs, 3 minus 1. Okay, and so now that here, again, I am going to navigate over to the other board and let's tear down the calculation. All right, so with that work I suggested earlier, f of 3 gives me 3 all square minus 1/3. Okay, because our function says, the rule of the function says the input square subtract 1 over the inputs. Okay, and that gives me a 9 minus 1/3. And then f of 1, according to the rule of the function, says we do 1 square minus 1 over 1. Okay, which is just a 0 for that. Okay, and so now rate of change in the end, let's continue from the earlier step. So rate of change at the end comes out to be, now not that n yet, okay, but in the next step, putting these pieces together, I'm looking at a 9 minus 1/3. This is f of 3. That's the result of f of 3. I put the final calculation here in a hold right there and decide to do the overall calculation there. Minus 0. Now, this is easy enough to see the answer here is 0 for f of 1. And so I put that 0 here. Okay, and then x2 minus x1, final x minus initial x, 3 minus 1 in the denominator. So it's always a delta y over a delta x. Okay, so the rule has always been delta y over delta x, or changing y over changing x. Okay, and so now this is going to be 9 minus 1/3 over 2. And so that answer here comes out to be 26 over 6. And we can reduce that by a common factor of 2, so it comes down to a 13 over 3 right there. All right, so that is our final answer. And once again, this is a positive rate of change. So you can think of this as a rise over run. It's a run right here, and it's a rise right there, because this difference in the y values gives me a positive change in the y values. And the overall answer here was positive. Okay. All right, so the whole purpose of that example 1 was to get anyone learning about this concept acquainted to the concept of rate of change. But now allow me to start explaining why, throughout my explanations, throughout my detailed explanations before the example, I was somewhere here and there using a few times the word rate of changes. I purposely put things in plural. And then now, starting with example 1 here, I start aligning with the standard, the proper term being used throughout all standard textbooks out there, which is, in rate of change in singular form. Okay, so why is that? So when I was delivering, and it's just my style, when I was starting out teaching about rate of change, okay, So the proper term now is rate of change. It's not rate of changes as I wrote earlier, but the reason I did that optional S right there, because when I was teaching, I really want to emphasize that anytime you are calculating a rate of change, there are always two changes. There are always two changes. The change in the y, and now allow me to use that shorthand writing, the change in the y over the change in the x. There are always two changes. Okay? But now, and that was the reason why I used that optional, the plural right there in my teaching earlier, prior to the example 1, to really enforce the idea that we always have to look for two changes, the change in x and the change in y. Okay, but now allow me to bring anyone back and align with the proper term being used throughout all standard textbooks out there. The truth now is that all textbooks only use the term rate of change in singular form. Okay, so there is a reason why. So it's all about the intention. It's all about the intention. So now when people say rate of change, and clearly this is a singular form. Okay, this is just one rate of change. So why is there a difference? It's not that I try to teach the wrong thing. So now here's the reason. When people say rate of change, there's an intention behind the scene. The intention here is when they see this change here. Obviously, I explained there were two changes. But when they say rate of change, the intention here is to look at the change in the function's output, the change in the function output. Because here's the thing, now at this point when anyone have learned enough and have grown enough majority in your understanding, then of course the change in y happens because there was a change in x. Of course we have the change in y because we had a change in x. Or in other words, the change in x caused the change in y. So for that reason, people particularly are interested in looking for the change in y. So this change right here is specifically this change in y right there. So that's the reason why throughout all applications out there of rate of change, when people say rate of change all of the times, they're saying rate of change in singular form because they intentionally looking for already. They're intentionally already talking about the change in the y value, the change in the output values of the function. Okay. And of course, it's automatically understood that behind the scene there has to be a change in the x values. And that is the reason why. So from now on, I'm going to start using that. I'm going to start getting myself back and align with that proper term being used throughout all textbooks out there. No longer rate of changes, but rate of change now. Okay? But that's simply because I want to first start out to emphasize that there are always two changes. It's a change in y, there's a change in x, okay? And then people specifically, now under that, our assumption that the y value represents the outputs of the function and the x value is the inputs, then people specifically, anytime people mention about the word rate of change, again, they intentionally mean the rate of change in the outputs. And so now that does explain a little, that actually explains even further that, because here's the thing, if we just seeing things if in the way how I was saying rate of changes, then we can also have a delta y over delta x, or we can even have a delta x over delta y, because this is the true rate of changes right here. Because you see, if we treat these changes of x and y independently, then we can set a ratio delta y over delta x, or we can also set a ratio of delta x over delta y. But why was the formula? See, I already led everyone into that path already. But why was the formula only chosen to be delta y over delta x? Okay, because as I said, simply having just two different changes in the x values, changes in the y values, we could have ended up with two different forms of a ratio between the two changes. But why did we specifically stay in this one right here, the delta y on top in the numerator of the fraction, and having the delta x in the denominator of the fraction? Simply because this fraction here kind of already tells already told the intention that people, anytime mentioning about rate of change, they're looking for the change in the output values, okay, per change in the input value. And so, of course, people have to automatically now understand that because there was already a change in x, that's why it's causing a change in y. And now we're specifically looking for the change in y. We're measuring how much y is changed, how much output is changed per units of change in x. Okay, and so that's the whole reason right there. All right, and so now from now on, it's all rate of change and rate of change. It's not rate of changes anymore. Okay, and so now there's one more highlight I would like to point out right here. And at this level, when you are viewing this video lesson as you are in a college algebra course, or you are in a pre-calculus course, college algebra or pre-calculus is really the same course. It's just being called differently depending on the school that you are at. Yeah. But there's a term that you got to watch out for. So I start out using the term rate of change. Okay. But now allow me to start looking all over and now introduce that term. All of those rates of change that you've learned so far from the beginning of this lesson to now. Another truth behind the scene, but at this point we don't have to be too worried too much yet about why they're calling it like that. But the kind of rate of change we have been learning is indeed referred precisely as the average rate of change. Okay, the average rate of change. In the end, it's a rate of change. It's how fast the change in the output versus the change in the input. Okay, how fast the change in the output per unit of change in the input. But now, to be even more precise, okay, all of those rate of change we have done, okay, this kind of rate of change right here. See, y2 minus y1 over x2 minus x1. Okay, final y outputs minus initial outputs over final inputs minus initial inputs. That rate of change right here, the truthful name, okay, the precise name is called the average rate of change. Okay, it's called the average rate of change. So in my teaching style, allow me to just refer to that as a name. So from now on, any of those problems that we're following with this formula right here will be precisely referred as the average rate of change. Okay, and then throughout our course right here, when you hear sometimes even if I skip, or sometimes even if any problem that you're looking at skip the term average, it really means the same, average rate of change or rate of change. That's what I'm talking about at this level right here that you're learning. Average rate of change or rate of change in general is exactly the same. I would like you to wait until your calculus course, and your calculus 1 professors there will be explaining precisely why there's an average rate of change, why this work right here is precisely and should be called an average rate of change versus any general rate of change out there. Okay, so again, at this level, there's not much difference between just simply any rate of change, okay, or average rate of change precisely. So a lot of times you will be asked to calculate average rate of change, which is this thing right here, or even if you see a loose term, rate of change, like that. It's just that term right here. It's just that formula to calculate. And then again, you will get a very clear explanation from your calculus professor once you arrive there after this course. Okay, to hear that explanation why this work here, this formula here should only be regarded as the average rate of change, because the actual rate of change is going to be used as something else in your future course of the calculus. Okay, but for now at our level, sometimes it's referred as rate of change, sometimes it's being precisely stated as an average rate of change. For now, it's a very same thing. Okay. All right, so from that point on, let's now look at another example. All right, so let's call that now example 2. Okay, and we are given another function. Let f of x be defined as a square root of x minus 2. Okay, x minus 2. And so now we want to compute or evaluate and now, each example I add on a little extra details right there where eventually it's all arriving at the formal precise name right here. So now I'm going to start using the precise name. Calculate the average, okay, the average rate of change, okay. All right, and now part A on the interval. All right, so the interval here is 3 to 6. Okay, 3 to 6. Okay, so what is the difference between this problem and in example 2 and the problem in example 1? Well, obviously we're working with a different function, but here I wrote that term average rate of change, and I would put that term average here in red ink right here to catch your attention that from now on throughout the rest of my the lecture here I will use this term a lot, but really it's just the way how we're doing that is just exactly the way how we have been doing throughout the previous examples. Okay, and so now that average rate of change, this is now the actual precise name of that, the way of how we're doing that. Okay, so now average, okay, rate of change. Okay, so instead of just simply generally rate of change, okay, now I add in that precise name average rate of change, but it's exactly the same thing. And like I said again, at this level there's no big difference, and there's not really much difference between the rate of change and the average rate of change. And then you will wait until your formal calculus course to hear the actual a real explanation about the actual difference between an average rate of change and a general rate of change there, okay, because there at calculus you will learn even a more advanced kind of rate of change, where that advanced kind of rate of change is being referred as just the general rate of change. Okay, so just for now we nailed this down that to do this it's just exactly like how we were doing in example 1 right there. All right, so the function output at the final, the final function's output minus the initial function's output f of 3. Okay, and we divide it by the difference between final input minus initial input right there. All right, so that's the setup. So like I said again, it is exactly that rate of change formula we were doing throughout the whole time. Okay, and just here I'm putting everyone back into that, putting everyone into a line. I'm making anyone learning in this lesson to align with the proper term that's being used throughout all standard textbooks out there. Precisely speaking, it's called an average rate of change. Okay, but to see why we're calling it that way, okay, you wait for a calculus course. All right, so now to proceed further with this problem. Now on this space of my other board right here, f of 6 is the square root. The rule of the function says that, with input minus 2 inside the square root. And so now input here is 6 minus 2, all that there is inside the square root. So we're looking at the square root of 4, which is a 2. Okay, and then f of 3, and believe me, one day when you are mature enough in doing your work, you don't even have to show this step. Okay, when your foundation has already been strong, you can just continue directly from the previous step. Right, square root of now 3 minus 2, input minus 2 in square root. Okay, that's square root of 1, which is 1. All right, so now continuing from the previous step, what we are looking at right now is the average rate of change. It's been the same rate of change. It's just been the same rate of change. That's we started with. Okay, and again, watch for that clear explanation about the difference between an average rate of change and an actual rate of change when you arrive at a formal calculus course. It's just here. We are in a pre-calculus course, so we've learned these concepts and we allow these terms to be a little bit loosely blend with each other. So right now at our level, being a pre-calculus, before calculus, right? Then average rate of change is, for now, yes, you can take that average rate of change is the same as just the general rate of change. It's the same as rate of change. Okay, so that average rate of change, we can calculate that by, so now it's going to be 2 minus 1 over 6 minus 3. All right, so now we have, and so the change in the y value turns out to be a positive, okay, and the change in the x values is always positive. Okay, so it's a 1/3, and this is, for this problem, it's a rise over run. Okay, it's a rise over run. Okay. And now let's look at part B of the example. All right. So now, once again, on the same function here, let's calculate the rate of change, the average rate of change on the interval. How about from 2 to 3? Okay, from 2 to 3. Okay, so that average rate of change equals, okay, so once again, the formal setup right now, f of 3, the final function's output, minus the initial function output, meaning f of 2, f at the initial input. Okay, and then now 3 minus 2. Okay, that's the setup. So from now on, really nail it down. This same function, I mean delta y over delta x, this same formula right here is the formula to obtain, in our class, sometimes here and there I call that generally rate of change, but it's the average rate of change, the same thing right now. Okay, and you can see there's a reason why I keep emphasizing that quite a few times up to this point already. Okay, but now let's continue with this calculation right here. And allow me to change the style a little bit. So that average rate of change really equals, now substituting in, so f of 3, substituting values in, we're looking at the square root of 3 minus 2. Okay, so I'm showing, in this problem, I intentionally go through the style of presenting the steps where people already mature in writing down in writing down the setup and don't need to write down the separate scratch work like that. Okay, and then so this is f of 3 minus the square root of 2 minus 2. Okay, and divide that by 3 minus 2. Okay, and so now square root, first term is the square root of 3 minus 2, but 3 minus 2 is a 1, so it's a square root of 1 minus the next term here is a square root of, so 2 minus 2 is a 0, so square root of 0 over, now 3 minus 2 is a 1. So we put all things into one in one fraction, but in each step we're advancing, in each step that we're moving, we're still working on each individual components of that expression. Okay, and so now we're looking at a positive delta y over a positive delta x right here, so it's another rise over run, positive change in y over always positive change in x. Okay, and so in that way, now the answer is just positive 1. Okay, that's another rise over run. All right, so that's the end of example 2 right there. And so now at this point right here, allow me to introduce the third example where we are anyone viewing this video is put into a slightly different situation. Okay, but we're still in the end evaluating the average rate of change, or just in general at our level rate of change. Okay. All right, so here we are at our example number 3, and this example here I'm going to say, all right, so I'm going to let f of x, okay, be represented, or let f of x be the function, whatever function that is, be the function represented by the given graph. All right, so now in that way, allow me to show the graph right here. All right, so here we go. Here's the graph of for this function. Okay, nobody needs to worry about what function that is. Is that an x squared or x squared minus 1 or minus x squared or whatsoever? Okay, the point is we have a graph, and with 2 given points like that. Okay, with 2 given points like that. And so each point here, okay, has and you can see that from the graph, you can see that it stays on the grid right there, which will eventually make it easier for us. But now, okay, so now with that 2 given points right there, so question A. Now I would like to use the following word. Precisely speaking, it should be asked as following: estimates. Because see, like I have explained earlier when we were still discussing about the graph of a function. Now, anytime we are reading the graph, instead of knowing the actual rule of the function, we only are given the graphical representation of the function, like in this case right here. Then the only best thing we can actually do is to estimate. We estimate values from reading the graph. But sometimes, admittedly, sometimes some textbooks, some professor might still use the term evaluate, which is completely fine. But we just need to automatically understand that when this term is used, but only the graph is given, our best work is to estimate. Okay, our best try is just to estimate the best that we can. Okay, so now we want to estimate or evaluate the average, okay, rate of change. Okay, that's the average rate of change of the function f of x. Okay, on the interval from 0 to 3. All right, so we want to estimate, and so indeed I wrote there's a little about 0 to 3. All right, so this is the interval, and the graph is still there, so I don't want my writing to be hidden behind the graphing screen like that. Okay, so let's now read the graph. Okay, let's now read the graph. The interval from 0 to 3 right here. See, this is the reason why I put those points on the graph, just to make it easier for us to see. But so now when we estimate, it's all about estimating. Okay, so let me turn into closer zoom of the graph right here. So now in closer zoom, when x equals to 3, when x equal to 0. So from x equal to 0 to x equals 1. From x equals 0 to x equals 3. Okay, then this point right here is about right there at x equals 0, and this other point is right where it's x equals 3. So in that way, we are going to estimate the outputs Okay, the output when x equal to 0, the output is 1, and this point right here is is helping us. But in real time, when we're doing these problems in real time, a lot of time we just gonna have to really look very hard to find the precise values. Okay, so for example, when it's being like a 3.5 right there, when x equals 3.5, then good luck finding the precise values. Instead of unless we have a very advanced tracing software or something like that. Okay, and so now getting straight into the problem. Then the way of doing that average, okay, rate of change. All right, the first thing to be done, we need to find, and so in this interval, final input is 3, initial input is 0. So 3 minus 0 in the denominator, but f of 3 minus f of 0. Okay, f of 3 minus f of 0. And that's just exactly the formula I've been introducing. Okay, but now to obtain these vertical values, these output values, we have to estimate through the graph. And that's the whole idea right there. So according to the graph, and I put it in closer zoom earlier, okay, in a full screen view right there, then f of 3 seems like, or estimated to be about 4, okay, and it's still there on the picture, okay, and then f of 0 was estimated to be about at output 1, okay, so 4 minus 1 over 3 minus 0. Okay, so everything now is completely an estimate, especially these two values right here, or specifically those two values. And so now, but in the end, we're looking at once we arrive at that estimate, then now we're looking at 3 over 3. Okay, 3 over 3, and it's a positive 3. So it's a rise over run. Okay, so now it's a positive 1. So the average rate of change on this interval changes where x changes from x equals 0 to x equals 3. The function was rising. Okay, rising what? Rising 3 units over 3 units run. Okay, that's an interpretation of that. Okay, all right, and so let's give it another try, shall we? All right, so now I'm going to erase this interval, and I'm going to call that part B right here. All right, so let's now, and let me hide these points away for now. Okay, so I just want students and viewers to focus particularly on the graph right here. So what we have is simply the graph. Okay, and so now in part B, we want to estimate or evaluate that average rate of change again of the same function with this graph right here. But now how about our interval here is from, all right, so how about from 2 to 4? Let's look at that interval. Okay, let's look at that interval. All right, so in this interval, now back on the graph. And allow me to put it in the full view screen right here. So when x equals 2, okay, because the interval is from 2 to 4, so at the initial value, okay, at the initial input right there. All right, then this is that point right there. So it's about right there. So this is about x equals 2. Okay, and then the final input is when x equals 4. Okay, and so now allow me to put in that other point right there. So these 2 points now reflects the 2 points at the initial input, and then this is the final input. So now with well, we are lucky that we have software, but see, without having a software, it's all about we estimate. Okay, if you're given just an actual printed picture from a textbook, from a whatever, then the best thing we can do is look through the picture and estimate and use the grids. Okay, and so in this case, it seems like when x equals 2, the function output is 1, 2, 3, 4, 5 grids above. But see, it's all about it's entirely an estimate. Okay, and then when x equals 4, the final inputs, the final outputs correspondingly is about 1 grid above, 1 square grid above right there. So it's y equals 1 right here. Okay, so in that way, now allow me to get back on the board and do that argument there and write down the setup. So the average rate of change, okay, the average rate of change in this case, and the famous formula ever, the fundamental formula ever. Now the final function's output, that is f of 4, minus the initial function output, that is f of 2. Okay, that difference in the y value, we're going to divide by the difference in the x values, 4 minus 2. All right, and so now, according to what we have estimated by looking at the graph, then it looks like it's estimated that f of 4 is about at height 5. So it's 5 minus, now f of 2, according to the graph, is estimated to be about 1. I just now realized I did the incorrect work right there. So I got things backward. Okay, so f of 4 is about 1 for the height right there. Whereas f of 2 is estimated to have the outputs being 5. So 1 minus 5 over 4 minus 2. Okay, so this is any one of these two values is completely an estimate. Okay, so I estimated, again I said that I estimated that f of 4 gave outputs 1 and f of 2 gave outputs 5 right there. All right, so now, but once we have accepted that estimates, right, then we come to we are ready to do the actual calculation. So now 1 minus 5 is a negative 4. Now we're looking at a negative change in y, So obviously the function was initially the function was higher, and then at the final value it's lower. And so now that's why it's resulted in a negative change. And then the negative change over the total change in total change in x values being 2. Okay, so now we're looking at an answer, the average rate of change here being negative 2. Okay, but this is the problem where this is the work where I refer to here as a fall overrun right here. Fall overrun, because we had a drop. This negative change right here is a fall. Okay, it's a drop in vertical value. So it's a fall overrun right there. Okay, and so now that's how we, the intention of this example is to get you, to give you that, ability to look at the graph and estimate the value, and from there figure out the average rate of change again. Okay, and so on my computer picture right here, yes, at those points what we have estimated was correct, but like I said, that's not the important part. It's all about we estimate. So even if your software is not able to give you the exact estimate as as the software I use here, then that's completely okay. All right, and now let's look at another example where I call that example 4. A different challenge. We're still calculating average rate of change, but it's a different situation here, a different case here. Okay, so I would call that now example 4. Let f of x be the function but represented by the given table. So instead of graph like example 3, now we have our function given and represented by a table. Okay, so you have seen all of these ideas back when I was still introducing the basic understanding about a function. A function can be given as a rule that you can see specifically throughout example 2 and example 1 here. Okay, or a lot of times of our function is, there is a rule, but it's given as already a table representation. Or just earlier we had a function that given as a graph. Okay, and so now we no longer need that graph picture there. Okay, so here's a table for example 4 right here. All right, so the table allowed me to use a column view right here. So the x is the inputs, okay, and the value for f of x or the output right here. So how about 1, 2, 3, 4, 5. Okay. So now these are the outputs here. So it's how about 8, 7, 6, 7, 8. Okay. So there's that table. These are the output values. These are the input values right here. Okay. So that's the table. And so now I'm very short at space. I'm going to move over to the other board right there and write down the actual question right there. Okay. All right, so question A right now. So here it's evaluate, and yes, it's the exact way. Evaluate the average rate of change on the interval between, the interval, how about from 2 to 3? Okay, so now we have that interval. This is initial input, this is the final input. Okay, but now in that interval of the change in the input values, what change, how much is the change in the outputs? And then at the end, we're calculating that as an average rate of change. Okay, and so in that way, average rate of change is now ready for that. Okay? And we use that famous formula. So average rate of change is the function, the final function output, f of 3, minus the initial function output, f of 2. Okay, that's why it's change in the y values. Okay, and we're dividing that by the final input minus the initial input. Okay, so f of 3 minus f of 2 divided by 3 minus 2. All right, so now the only thing that this problem is different with any of the earlier ones is that now we're going to look it up from the table for these output values. So instead of using the rule that's explicitly written in the function, like what we've seen in example 2 and example 1, to use a rule to calculate these outputs. The only way to calculate, to look at the outputs here, the only way to determine the outputs here is to look it up from the table. Okay, so now on the table itself, back to the table. Then when x equals 3, this is the final value. When x equals 3, our final output is 6. But when x equals 2, our final output is 7. Okay, so now in that way, I'm looking at 6 minus 7 divided by 3 minus 2. All right, and so now in that way, I'm looking at a negative 1 over 1. So we're here, for this particular interval, the function is giving a fall over run, which is indicating a negative change over that amount of run, that amount of run being a positive 1, okay, or a negative 1 rate of change, an overall negative 1 rate of change. All right, so it's just how simple that is to calculate this. So let's do one more problem. But now when we get into this next problem, I want anyone learning with me to work through the problem as independently as possible. Okay, so how about let's call that part B right here. Evaluate the average rate of change on the interval. So now let's do that. How about from 1 to 4? Okay. All right. Initial inputs, final inputs. So just that exact same setup that we've been using. So now I'm going to look for the final function output, which is f of 4, minus the initial function's output, which is f of 1. Okay, and then we're looking at divided by the change in the input values, 4 minus 1. Okay. Yes, admittedly, someone may be a little worried about what about the 2 and the 3 between this, but that's not something to worry about because the interval here is from 1 to 4. Okay, the interval is from 1 to 4. And so now, f of 4 from the table, f of 4 is a 7. So this is our final output. F of 1 is an 8. This is our initial output. Okay, initial output is here. Final output is here. Okay. And so now in that way, 7 minus 8 divided by 4 minus 1. Okay. And now we are looking at, so 7 minus 8 is a negative 1, of course, over 3. Okay, so the change in x is a positive 3, always. I mean, always a positive. Okay, but the change in y in this case is indicating it's a drop in value. Okay, it's a getting lower in value. So in the end, and this is our final rate of change. It's a negative rate of change. So you can also see this. You can also understand this as a fall over run. Okay, so sometimes it's rise over run. Sometimes it's fall over run. It all depends on how our final sign of the rate of change here is indicating. Okay,